All right, so welcome to Chem 2045 live online. My name is Julie Emerson, and my contact information is posted for you here. My office phone number 727-712-5450. If you call the office and I'm not there, you can leave a message. It'll go straight to my email, and my email goes to my phone, so I'll get the message pretty quickly. If you want to email me, obviously through my courses is quick. It will forward to my Gmail, which also goes right to my phone. So I get that pretty quickly. And then, of course, my SPC email, which is emerson.julie@spcollege.edu. That also goes right to my phone. So I try to get back to you as soon as I can. The only thing I'll say is I am an early riser, early to bed, early to get up. So I usually shut things down at about 8:30, 9 o'clock. And then I have a little bit of downtime, just to read and not think about work. So if you email me after 8:30 or so, I probably won't get back to you until the morning. But I'll get back to you as soon as I'm back on. And that includes the weekends. To me, a Saturday is just like a Tuesday. I still check my email. I can still do Zoom sessions. I still work. If you want to meet me in person, my posted office hours in Lyceum 216 on the Tarpon Springs campus are Monday 11 to 2. Tuesdays and Thursdays, I'll be on campus 8:15 to 9 o'clock. I have a lab that meets at 9 o'clock, probably be done by 11. So then after lab from 11 until my lecture at 12, I'll be in my office. And then after that lecture, 1:15 to 2:30. That's Tuesday and Thursday, same schedule. And then Friday, I have sort of kind of flex hours. I won't be on campus Friday unless you request to meet with me in person. And the 11 to 1 is also flexible. So if you need to meet with me in person on a Friday, just send me an email and we'll make it happen. But I won't be on campus on Friday unless somebody asks me to be there. So just if you're gonna come, make sure I know you're coming. Otherwise, I'd hate for you to show up and I'm not there. Virtual office hours. So in our base schedule, we're only allowed to have 5 virtual office hours. So these are the ones that I've posted, but they're very flexible. For y'all, Tuesdays and Thursdays before class is a good time. If you need to meet with me after class, I don't have that posted, but we can make that happen. I have the live online lab from 4:30 to 5:30 before class on Tuesday. So I even have some time before lab, so like 4 to 4:30. But really, the virtual office hours, they're very flexible. So if those times don't work, I also have Wednesday blocked out from 10 to 1. But again, if you need to meet with me on a Monday night or something, just let me know. We'll make a time that works for both of us. So that's my contact information. No questions so far. So now I'm going to get into sort of grading and procedure and how this is going to work. So throughout the semester, we're going to have 12 chapters. And what you're going to find is in each chapter, I'll be honest, there's a lot of information in this class. There's a lot of stuff. So in each of the chapters, you'll find my class notes. So what you'll notice tonight is as I'm going through the lecture, just like my face-to-face students might remember from intro chem last semester or the semester before, is I just follow my chapter notes. So if you want to print them out ahead of time and then just follow along with me, they're right here. You just go into my courses, go to the chapter 1 folder, and then the first thing that's posted is the notes. So you can print those out and then just sort of follow along with me if that's what you'd like to do. Then what you're going to have is your practice quizzes. Because you are taking the class online, you are sort of learning a lot of this on your own, and practice quizzes are a great way to do that. So what I try to do with the practice quizzes is break them up by topic so that you're not doing all of the chapter in a practice quiz. There might be a little part about chemical physical changes, then there might be a part about element compound mixture. And then that way, if you're struggling with one topic, you just can take that practice quiz over and over and over. You don't have to take the entire chapter over and over and over again. So that's why there are usually for each chapter anywhere from like 2 to 4 different practice quizzes because I try to break them up by topic. The practice quizzes, you can take them as many times as you want. I want you to do it so they do have a point attached. So they are each worth 1 point. There's going to be 30 of those over the semester. So there's going to be 30 points total from the practice quizzes. So a lot of times students just kind of neglect to do them. Please do them. They have a little bit of point value, not a lot, I admit that, but the other good reason for doing that is that the practice quizzes will prepare you for the credit quiz. So the credit quiz in each chapter, this one is a little bit different. It will be graded. They are 25 points. They're timed, right? So there's a little bit more to the credit quiz, and that does cover the entire chapter. But if you've done well on the practice quizzes and you've done them as many times as you need to get a good score, then more than likely your credit quiz is going to reflect that. So success on the practice quizzes usually predicts success with the credit quiz. And what I'll do, there's going to be 9 credit quizzes. So not all chapters have a credit quiz. I'll explain that in just a second. There will be 9. Each of those are 25 points. I am going to drop the lowest one. So your 8 best quiz scores is going to total 200 points. All right. Then we are going to have 3 exams and a final. So there's exam 1, 2, and exam 3. And then at the end of the semester, of course, we've got a final. These are 200 points each. So we have a total of 800 points from the exams. Now, the way that I have this is if you miss a quiz, it will not hurt you, right? Because I dropped one of your quizzes. If you miss more than one quiz, that's when it's going to start to help you. But there is some extra credit in the course that would make up for an additional missed quiz if you did miss one. The exams, I don't drop an exam, but the final exam will replace the lowest test grade. So if you do miss a test for any reason, honestly, if you're going to miss a test because you're sick or you're out of town, as long as you can provide me documentation and do it quickly, like don't wait 3 weeks and then tell me. I need you to tell me within a day or two, and there's documentation that would justify missing the test, then I can work with you on that. But otherwise, if it's not really an excusable documented reason for missing the test, then what'll happen is at the end of the semester, your final exam will just replace that 0. So it'll count twice in your grade. The other thing is your final exam will replace your lowest test grade as long as it's a higher score. So if you've taken all of your exams, but let's just say you bombed test 2 because you had a bunch of other tests that week, the final exam, as long as it's a higher score, it will just go in and replace that test 2 score. So final exam replaces lowest test grade. But again, only if it's a higher score. If your final exam is your lowest score, then it's only going to count once. All right, so that's how the point distribution is going to work. It turns out to be like 1,030 points. Easy, 90% gets you to an A, 80% gets you to a B. Now, the extra credit that I was talking about, that's going to come from the Pearson website, which is the textbook. And I haven't heard a lot of complaints about these, so I think that they work really well. These are called dynamic study modules. They changed it from guide to modules, and I just did that. So dynamic study modules. Each chapter has a dynamic study module. But these are on the Pearson site, and I'll show you where those are here in just a second. And each one of those is 5 points each. Now, it's typically 1 per chapter, but in chapter 3, there's actually 2 because it's just a lot of content in chapter 3. So it actually turns out that there's going to be 65 points, and these are bonus points. These are extra credit points. So remember how I said if you miss a quiz, it won't hurt you because I dropped the lowest quiz? Well, let's say maybe you missed a second quiz. As long as you're doing your dynamic study modules, that would easily replace another missed quiz. But you definitely want the bonus points, right? Like if you had me for intro chem face-to-face, I always put a little extra credit on the exams. That's really what I'm doing here. This is the extra credit that you would have on your exam. The My Courses Learning Management System isn't great about putting bonus points on a test, so I just do these separately. Now, these bonus points, this is the other thing. It is the extra credit for the test, but I don't label it as the test extra credit because if the final exam replaces your lowest test grade, I don't want your extra credit points to go away. So those bonus points just sit separate, and that way, once you earn them, you never lose them. Honor Lock is not going to be used at all. We've switched to Respondus, and Respondus is only going to be for the exams, not for the quizzes. So the quizzes are timed, but they are not proctored. So timing a quiz is one way of assessing how well you know the material. So definitely you have to know it well enough to answer it in the required amount of time. The exams, however, those will be proctored. So for each of those exams, the exam 1, 2, 3, and the final, that's where you're going to use the Respondus proctor. And I'll show you in the class here in just a little bit where you can take a practice Respondus test just to make sure your system is functioning and agreeing with Respondus and you know how to do a room scan and all that good stuff. And I'll show you that here in just a little bit. Okay, so remember those dynamic study modules, do not forget those. What'll happen is before the test, the night before the test, for example, exam 1 is chapters 1, 2, 3, and 4. So chapters 1, 2, 3, and 4, bonus points, dynamic study guide modules, they're due the night before the test at midnight. All of this is on the course calendar, and I'll remind you of this as we get close. I'll say, hey, this is what's due. Normally when we start our Zoom sessions, I'll have at the top of the paper, this is what's due coming up. So just make sure those dynamic study modules, they close the night before the test for the corresponding chapters that test is on. All right. One question I always get is, can I exempt the final? So if you have above 90% on all exams and your credit quiz total. All right, so that means, again, your best 8 credit quizzes. So you've got 180 out of 200 points for those 8 best credit quizzes. So again, if you miss one quiz, you're still in the running to exempt, as long as you have above a 90% on all the exams and a 90% on your 8, not on each individual quiz, but on your quiz total. But the 90%, it has to be on every exam. It's not an average. It has to be an A on every exam. If you meet that criteria, you will be exempt from taking the final exam. All right. So as we get going through the semester, if it looks like you're in the running for that, if you are exempt, I'll send you an email to let you know. And I usually have at least a handful of students that exempt, so that's always nice. Now, as I mentioned, there's 12 chapters, but only 9 credit quizzes. So you might be wondering how that's going to work. So for example, exam 1 covers chapters 1, 2, 3, and 4. There will be a credit quiz on chapters 1, 2, and 3. All right, when you take exam 2, it covers 5, 6, 7, and 8, and you'll have a credit quiz on 5, 6, 7. And then exam 3 covers chapters 9, 10, 11, and 12, and you'll have a credit quiz on 9, 10, and 11. So the reason why I did that is once we finish chapter 4, the following week is going to be the test. So I don't want you to have to worry about a quiz for chapter 4. I just want you to start worrying about the test. So the last chapter that we cover for that particular exam, there will only be practice quizzes to help you, but not credit quizzes. So these are your 9 credit quizzes that you have. And I don't think there will be any confusion. You'll see it laid out in each of the folders. All right, so that's our grading distribution. You got my contact information at the front or at the very top. So now what I'm going to do really quick is share my screen and then just show you mostly what you probably want to know is that Pearson website. So when you log into my courses, you can go, obviously you found the Zoom link, the Start Here folder, that's what I'm looking at first. So read the course syllabus. We went through most of the information right now. The first day course materials, that's where you're going to find those extra credit assignments. So that's what I want to show you. So our first exam is September 12th. And again, it covers chapters 1, 2, 3, and 4. So those extra credit study modules on the Pearson site are due the night before, September 11th at 11:59 p.m. So students do this differently. Sometimes as we go through chapter 1, to sort of practice the material, students will do the dynamic study modules as we go. And then chapter 2, they do the chapter 2. Some students save the dynamic study modules as a way to prepare for the test. So they save them more for closer to the exam. I actually recommend doing them as the same time we're doing them in class. So as we go through chapter 1, once we're done, go do this dynamic study module. Then when we do chapter 2, go do the dynamic study module. Because I think what happens is that sometimes students underestimate how long they take. And then it's the night before the test and you got to get them all done and you don't have enough time. And they are things that if you, as long as you do them, you give the time to them, you should get full points. And I want everybody to get the bonus points. Plus, I think it's a good way to go through the chapter. All right. Then there's a couple of links here. So if you want any tutoring or you want to make an appointment with a tutor, there's a link here for the Learning Support Centers. You can schedule an appointment with a tutor there. All right. And then now let me go back here and show you the textbook. That was the important part. So right on the course content, you'll see this first day course materials. When you click on that, this class, I think a lot of classes are doing this now, so you probably are used to it. The textbook is inside the My Courses course, right? It's right here. So when you click on the first day course materials, right, it says right here, course materials, and then I specified this is your book, right? So we're going to click on that. All right. And then you got to click on some more. So I always think everything is so clicky. All right. So then we're going to launch courseware. So once we launch the courseware, then this is where it might look a little bit different for you. But what I have here is on the home page, you have the assignments right here for student links, at least for me, or we can open up the textbook because there are some things I want to show you here. So in each of the chapters, I do suggest specific homework problems from the book. So what I would want you to do is go to the e-text, right? The Pearson e-text, which is your book, and then open my book, right? Another click. So now we've opened up the textbook. And then when the textbook opens up, you'll get a table of contents. And that's right here, the dash line. And so let's say we're reading through chapter 1. Okay, so let's go take a look at chapter 1. You can go through the book, read the book, look at all the examples, right? There's a lot of stuff here that you can do. It's really a great book. But those homework problems, right? So the ones that I assign and trust me, I've gone through them and I say, yep, these are good to practice for the test. What you'll do is at the end of the chapter, right? Just like if you had the book as a hard copy, you'll see at the end, it says exercises. So if you click on exercises, the homework problems that I suggest, they're coming right from here. All right. Then if you want to check to see if you got them right, you can go to the end of the book, right? You know how the answer key is always in the end. I don't know why they called it back matter. Like, why didn't they just call it answer key? I don't know. They didn't ask me. If you click on back matter, then you go here and you say, okay, answers to selected exercises, right? So then those are those exercises that we looked at. And then you got to scroll through. If you don't want to do all that, the other way that you can check your answers is if we go back into my courses, go back into the table of contents. All right. And then, sorry, it's getting slow. There we go. If I go into my chapter 1 folder, all right. So chapter 1, first thing, those chapter 1 notes, that's what I had just showed you a little bit ago. So that's what I'm going to be working from tonight. So the notes, feel free, follow along, print them, not print them, whatever you choose. But this is what I'm going to be using for every lecture. Those homework problems that I said would be a great thing to practice in the TRO textbook, that's listed for you right here on the My Courses chapter 1 folder. So these are the ones. If you want to check your answers, you can go to back matter, or here's my answer key. So for a lot of the problems, this is something that I remember being frustrated with sometimes as a student. You have a mathematical problem, you solve it, you go to the back of the book and it's a number. That's all you get is the number and it doesn't match your number. And you're like, well, I don't know what I did wrong. How did that happen? So if that happens, what might work better is you pull up my answer key because I've shown the work, right? So I've shown you exactly how I did it. Sometimes I put little notes, right, on, all right, how many sig figs should it be? But anyway, you can follow my answer key because that might be a little bit more helpful. All right, so those TRO homework problems again are going to come from the Pearson book. There's the answer key, the Zoom that we're going to be doing. What I've done is I've left my Zoom sessions in for my summer class. If you want to work ahead, you certainly can. But as I go through the course and I record these Zoom sessions, I'm just going to replace the ones that are already there. So if you're working ahead and it says something about a due date, you probably have to ignore it because I'm sure it only applies to my summer class. But if you are on pace, right, then these Zoom session links, they're going to match what we're doing every Tuesday and Thursday night. All right. Now, the other thing I did is to try to segment the videos again, so you don't have to watch an entire hour and 15-minute video. Maybe you just need to look at sig figs again. I tried to break up videos based on topic, just like I did with the practice quizzes. So that might help you if you just need to remember or revisit how to do conversions, right? You don't need to remember how to do matter and changes of matter. You just needed a little more repetition with conversions. Then there's a video here just on conversions, or there's a video just on sig figs. All right. There are often in the chapter folders, there are worksheets. I definitely recommend doing them. It's added practice for you. The more practice, the better. And then the practice quizzes, as I mentioned, these are here for you. And you want to make sure that you take those as many times as you need to get full credit, and then take your credit 1 quiz. As I mentioned, the credit quiz is timed. You have an hour, which is usually enough time, right? And I will grade these by hand. Some of the practice quizzes will need for me to be grading them by hand as well. Now, most of the time, the practice quizzes will stay open the entire semester because sometimes at the end of the semester, students want to redo them to study for the final. Because the attendance policy for SPC changed, I had to have something due our first week for attendance. So this first practice quiz, which is probably going to take you about 5 or 10 minutes, this is going to be due Sunday at midnight. But that's the only practice quiz that's due. Your credit quizzes are always due Thursday at midnight, but we don't finish chapter 1 until Thursday. So it's next Thursday at midnight. So not this week, but next week is when your first credit quiz will be due. I've done it that way so that they're due Thursday, I grade Friday. So that's why I did it. And I tried to offset it so it wasn't the same due date as the lab. So you didn't have a bunch of stuff due on the same night. All right, so hopefully this is all really easily laid out for you. If you do have questions though, please reach out and let me know. Again, the big thing here is that Pearson e-text. So just make sure when you go into the Pearson site, your e-text right here, that'll get you to the book. But then also if you want to look at your assignments, the student links to your mastering, and in fact, I think it's going to auto-populate as soon as you log in. It'll tell you your mastering assignments that are going to be due. And again, they are the dynamic study modules, and you'll see the due dates here that match the due dates that we have on the course calendar. So and I don't know why these are out of order. It'd be nice if well, actually, I probably can do that. Yeah, look at that. So chapters 1 through 4, they're going to be due September 11th at midnight. The test is September 12th. All right, so these are the extra credit. So don't forget about these. It's 65 bonus points. That's quite a bit. All right, so that's the Pearson book. Let me stop sharing my screen. And okay, so the question was, credit quizzes are not proctored. Are we allowed to use notes? Yes. All right, so for the credit quizzes, it's not proctored, it's timed. So you can use your notes. You just have to make sure you know where everything is, right? If you spend too much time looking for what your answer will be, it's going to slow you down. So you still want to be pretty good with the chapter. Honestly, the way I used to study for tests, and this is obviously you may do it differently, But what I used to do for my exams is, okay, I've got my class notes, right? I've done my homework. Then what I would try to do is, as I was going through the homework, I would kind of highlight the things that maybe I had a problem with in my notes. I'd put a little star next to it. And then what I used to try to do, and I even did this in organic, is I would try to have like one piece of paper for each chapter with every, like all the like main pieces as a review, like an outline on one sheet of paper. Any formulas, if there was a really difficult homework problem, I might put some information here. Like all of the main points of the chapter, I would try to put it on one sheet of paper. And I imagine for your credit quiz, that might be a great thing to have in front of you. So you're not hunting for things. It's just right there on that one sheet of paper. The time it takes to go through your notes, the homework, and consolidate that onto one piece of paper, that is studying, right? It's organizing, it's studying. It helped me a lot as a student. That was sort of my way of doing things. But you obviously, you do you, right? All right. So no other questions have come in. You're very welcome. So what I'm going to do is I am going to get started with the chapter 1 notes. If you were able to print them out ahead of time, fantastic. If not, just maybe for Thursday, but you may just take notes on your own. You may not need these. In the past, I've had on my evaluation, students just say, she goes kind of fast. She talks real fast. So I'm trying to slow it down a little bit. And I think having my notes already done has helped a lot because then students don't have to write so much. You just have to kind of follow along with me. Okay, so what you're going to notice is if you had intro, a lot of this, you're going to be like, I just had this in intro. Why am I doing this again? So here's the thing. Intro is going to be covered in about 6 weeks. So we're going basically double pace and the rigor is going to be harder, right? Because it's Chem 1 rather than intro. So your type of question, the rigor of it is going to be a little bit harder. But a lot of the content, reactions, stoichiometry, gas laws, you've seen it. We're just going to do it again, but we're going to make it a little bit harder. So having intro is definitely going to help you here. If you have any questions about that, let me know. But some of this, especially this first chapter, you're going to be like, I've seen all this. For example, chemistry, right, is the science that seeks to understand the behavior of matter. And I think, in intro, we just said it's this science that studies matter, right? It's the study of matter. The changes of matter, right? Reactions, right? Matter is anything that has mass and takes up space. Kind of classic example, you've probably seen it before. We've got 3 states of matter. We've got solids, liquids, gases, right? So a solid has fixed volume, fixed shape, right? So if we think, and I'm not a good drawer, so you're going to do much better than me, but we've got our cube, right? Fixed volume, fixed shape. If it's a liquid, now we've got flexible shape, right? Because you could have a bottle of water. Let's say it's a liter volume. If I pour that bottle of water into a bowl, now it takes the shape of the bowl. So the shape is flexible, but the volume didn't change. It would still be a liter of water. Gases are flexible for both flexible shape, flexible volume. It's very easy for a gas to be condensed, to expand. So gases are flexible for both. Now we'll learn at the end of the semester, it's because of what are called intermolecular forces. How well those forces are holding the molecules together helps us understand why it's a gas versus a liquid versus a solid, but that comes later. All right, so matter, classifying matter. We can classify matter as either a pure substance or a mixture, okay? So I actually just did this in my intro chem class earlier today. So there's a lot of overlap. A pure substance has constant composition, meaning all samples are the same. Whereas a mixture has variable composition. Not all samples would be the same. So that's actually sometimes the question that you want to ask. If you're being asked, is this a pure substance or a mixture? Unfortunately, a lot of times when we hear the word pure in sort of like sales and marketing, it's to denote that it doesn't have contaminants in it, right? But for a chemist, pure means that it is purely one thing. And that one thing could either be an element or a compound. So for example, it is just a sample of iron. That's a pure substance. It's only iron. There's nothing else in it. That is a pure substance. or it is just a sample of carbon dioxide gas. There's no air in it, no oxygen, nothing. It's just pure CO2. So a pure substance to a chemist means that there's only one element in the sample or one compound in the sample. And because of that, every sample of that compound should be the same. Every sample of that iron element should be the same. The variable composition comes in when we take elements and compounds and we mix them together. And that mixing can produce a homogeneous mixture where it looks the same throughout, right? So easy to remember, right? Homo meaning the same. So homogeneous or homogeneous mixture. Whereas if it's heterogeneous, you're going to see different phases or substances. You'll be able to tell it apart. So let's say I took sand and added rocks and I try to mix it together. It's never going to mix uniformly. You're going to still see the sand and the rocks, right? So that's heterogeneous. Oil and water is the classic. But if I take salt and I put it in water and I dissolve it really well, all the salt dissolves, it's going to look the same throughout. So that would be homogeneous. All right. So pure substances have constant composition. All samples are the same. Element, that is our simplest form of matter. That is what I always love about this. Like chemistry to me is part foreign language. So everything we study in chemistry goes back to the periodic table. Those are our building blocks, right? Everything, all matter is made up of just those elements, right? That's it. So periodic table, this one has some stuff on it, right? But those are our building blocks of all matter, everything we study in chemistry. And then a compound is when you take two or more elements and bond them together. And a molecule is the smallest unit of a compound, just like an atom is the smallest unit of an element. So just terminology, right? You have atoms of iron, not molecules of iron. You have molecules of CO2, but not atoms of CO2, right? An atom is singular. Molecule is when two or more elements are bonded together. So just terminology. Mixtures, variable composition. Not all samples would be the same. Homogeneous, again, is when it appears the same throughout. Heterogeneous is where you can see the different substances within. Chocolate chip cookie, one example. All right. Then if we go to the next page, every science book is going to start with the scientific method. Okay. So that always has to be covered in there. So scientific method, sometimes, or sorry, not sometimes, but a while ago, a student asked me, like, what do you think makes somebody a scientist? That was a good question. I kind of thought about it and I was like, I think you just ask a lot of questions, right? You just want to understand and kind of be able to answer some questions, right? And so that's the scientific method, right? You have an idea. You want to figure it out. It's kind of a solution to a problem maybe, but you have an idea of how something might work. So, and that's usually based on observations, right? You make observations and then you start to wonder about an idea, right? Then you need to test it. So you design experiments to test your hypothesis. You collect your data, you analyze the data, right? And then you can make some kind of result from that, some sort of opinion based on what your data showed you. And then that has to be replicated over and over and over again before it ends up in a textbook, right? Before it becomes a theory. All right. So there's your scientific method. Makes sense. Then if we look at studying matter, we've got properties and changes of matter. Properties just describe the matter, right? A change obviously changes, right? But property is just used to describe the matter. So in both cases, property or change, we can have physical or chemical. So a physical change changes the appearance of the matter, but it doesn't change the composition. So what does that mean? It means that if I have water and I boil it and it turns into steam, I've changed the state, but I haven't changed the H2O molecule, right? That molecule looks exactly the same. I got an oxygen center bonded to two hydrogens, and that molecular structure does not change. The only thing I've done is I've changed the appearance, and in this case, the state. Dry ice turning into fog, that process is called sublimation, where I take it from a solid to a gas, right? So again, just another state change. So when I was learning this the first time, I thought, okay, physical change, that's basically a phase change. That's the easiest example. All right. But what's key here is no new matter is formed. So if you look at your equation, your structure of your reactant and the structure of the product hasn't changed. No bonds have been broken, no rearrangement of atoms, right? Everything looks the same. We've just changed the state. Another example is if I take salt, sodium chloride, solid, and I add it to water. We talked about it dissolving. The state now becomes AQ because it's in aqua or water, and the water is just still there, right? So if you notice, my two reactants look exactly the same as my two products. So again, there's no new matter here. And so that is the thing that you look for to say, oh, this is just a physical change. In a chemical change, bonds have to be broken, the atoms are rearranged, and new bonds are formed. So we always create new matter in a chemical change. And you can see that in the reaction equation. So like in this one, we take elemental iron, we add oxygen from the air, and it turns into ferric oxide or iron 3 oxide. So we can see, yeah, law of conservation of mass says we just have iron and oxygen on both sides. However, we took separate elements and made them into a compound. So clearly we formed new bonds. In this O2 molecule, that bond had to be broken before we could make the iron 3 oxide. So reactants and products look different. And that is your signal that you have new matter, right? Because your reactants and products look different. All right. So a chemical change is also called a chemical reaction, right? And it always results in new matter being formed. Sorry, that C came out terrible. All right. That's supposed to say reaction. Okay. All right. So those are changes. Physical change, just phase change. Chemical change is an actual reaction. You'll see that in the equation that you've got new matter formed. A property is just describing the matter. So a physical property describes the matter without doing anything to it. So all we have is like a sample of pure water. Let's describe it. So it is a liquid at room temperature. It is a colorless liquid. It's odorless, right? The density is 0.998 grams per milliliter at room temperature. We're not doing anything to the water. We're just describing the water as it is without touching it. A chemical property, on the other hand, is we're going to describe the chemistry. So what we're going to say here is we're going to describe what happens to the matter when we add something to it, or we do something to it, or we heat it or expose it to energy, right? So a chemical property, typically what it'll do is it will typically describe a chemical change. However, not always. An example with that would be unless it's a non-reaction. So what does that mean? So we know that, like, for example, some metals, if they're exposed to oxygen over time, they will oxidize. Some go really quickly, some take a little bit longer. And then there are some metals that don't at all, like gold, right? Platinum. That's why they're so good to wear for jewelry. So if I say that platinum, PT, is added to O2 and nothing happens, nothing changes, that is still a chemical property because we're describing the chemistry. And the way that you can think about it is we're adding stuff to it. We're manipulating the platinum. We're either like exposing it to energy or we're adding other matter to it and then describing what happens. Most of the time, a change will happen. And so a chemical change, a chemical property just describes that change. For example, sodium metal, if I add it to water, it starts to bubble vigorously, right? Platinum, if I add it to water, doesn't do anything. Those are both chemical properties describing the sodium and platinum, respectively, right? In one case, we had a change, and the other case we didn't, but we're still taking those substances and trying to we're adding something to it. The physical property, we're not doing anything to it. We just have this sample. We're just describing the sample. That's it. We're not doing anything to it. So that's the difference. So if we look at some examples, all right, and this is where you will like have things to write maybe as you go through the notes with me. Let's talk about these. The evaporation of rubbing alcohol. So your isopropanol that you have probably in your medicine cabinet, the evaporation, right? That is when you take liquid and change it into a gas. That evaporation is just a phase change. And so what we talked about, phase change means that this is just a physical change. It's not going to result in any new matter formed. We're just changing the state. If we burn propane gas, burning is very hard to undo. And when you burn something, new matter is always formed. All right, we're not heating something to boiling, right? That we're actually burning it, right? So that's a combustion reaction. You might remember those from intro chem. So combustion, this is definitely going to be a chemical change, right? Very hard to undo. All right. If you bleach your hair with hydrogen peroxide, also very hard to undo. So sometimes you may not know exactly, molecularly what's going on, but because it is very hard to undo, that is typically because you have gone through a chemical change. All right. Plus, the fact that we're adding a chemical to it and we're getting this outcome makes me think, right, that this is a chemical reaction. It's a chemical change. Remember, a physical change is something where it's by itself and you just change the appearance by like a phase change. Again, you're not adding anything to it. Whereas if you're bleaching hair, you're adding the hydrogen peroxide. All right. Formation of frost on a cold night, right? So we're just freezing. We're going to take the water and turn it into ice. So just a phase change. All right. A copper wire hammered flat. It's still a copper wire, right? We've just changed the appearance of it. That's actually malleable, right? That you can beat it with a mallet. That is a characteristic of metals. So the fact that it's hammered, that's just a physical change. We're not adding any matter to it. We're not adding any energy like light or heat. We're just changing the appearance of it. So that's a physical change. All right. A match ignites when struck on a flint. All right. So again, this is burning. This is a reaction. So this is going to be a chemical change. All right. So there's some more examples of chemical and physical change. I don't see any questions in the chat, so I'm going to keep going. But again, if you have questions, please let me know. All right. So we've talked about matter, how we classify matter, how we describe matter through either physical properties or chemical properties. Now we talk about energy. We're going to have a lot more energy in Chem 1 than we did in Intro Chem. So in Intro, we did talk about endothermic versus exothermic, very, very little, just a little bit. But now we're going to have Chapter 7, which is one of my favorite chapters. It's called Thermochemistry. So it's all about the energy of reactions. So in a reaction or a physical change, it could be either one, could be a chemical or a physical change. As that change occurs, energy is either absorbed or released. So if you imagine like, if you hurt your back and you go to the store and you get like a hot pack, right? A lot of times it'll be a packet of something inside. You don't necessarily know what it is. And there's like a tube inside. It tells you to break the tube. You'll hear it snap. And then you kind of mix it around. So what's happening is inside that tube is a chemical. When you break the tube, the chemical releases to whatever's surrounding it. And then as you squish the packet around, that substance as it's dissolving It's an exothermic process and it's releasing heat and that packet warms up. That's a hot pack. So exothermic is when heat energy exits the reaction. Okay, I always thought that was nice. Exo means exits, right? So your test tube or your surroundings, whatever it is, the pouch, right, itself, whatever that surrounding substance is, the surroundings will heat up because as that reaction or process releases heat, the surroundings absorb the heat and that's why they heat up. All right, so exothermic, that energy exits. All right, endothermic is the opposite. If it's an endothermic process, right, this is when you have your surroundings are going to cool down. And the reason for that is in an endothermic process, that change, whether it's physical or chemical, the heat energy from the surroundings flows in to the reaction. So when the example I always use is if you take water and evaporate it, we know that in order to do that, right, you have to put it on the stove and boil it, right? So that means that in order for the liquid water to turn into a gas, it has to absorb energy, right? And that makes that an endothermic process. So this, right, evaporating water, we've got to turn the stove on. We supply the heat. That heat goes into those water molecules, breaks up the intermolecular forces, and then allows the molecules to separate into the gas phase. So endothermic, we had to supply the heat. That means heat is a reactant, right? It's flowing into that process. So it's absorbed by that process. It's required. And so when you get out of the shower, if you're always wondering why when you first get out of the shower, you always feel cold. It's not that someone just dropped the thermostat 10 degrees, right? You're cold because all the water on your skin is evaporating. And that it requires energy for that to happen. And that energy is coming from your body heat. And that's why we sweat. That's how we keep our body temperature where it's supposed to on a really hot day, is that as you sweat and the water evaporates, it takes some of your body heat with it. And that keeps our body temperature where it should be. All right, energy, some definitions here. Energy is the capacity to do work, where work is defined as the action of force through distance. Not too worried about that, but kinetic versus potential, we'll probably get to more of this later. Kinetic is the energy of movement, so that's a good one to know. Potential is the energy of position. All right, and then thermal is associated with temperature, right? That makes sense. Thermal is temperature. So it's associated with the temperature of an object, and it's a form of kinetic energy. The reason for that is that temperature really is just a measure of molecular movement. So the higher the temperature, the higher the movement, the higher the kinetic energy. So thermal energy, right, is associated with the temperature of the object and is a form of kinetic energy. Okay, so those are just some definitions along with endothermic and exothermic that we want to know about energy in this first chapter. Also, law of conservation of energy. As you go through any kind of change, energy cannot be created or destroyed. It can go from what's called the system to the surroundings, right? The reaction to the surroundings, or vice versa. But it's traceable. It's not like energy just comes out of nowhere, right? You know where it comes from. All right. So that was kind of some basic conceptual stuff. Now we're going to get into math a little bit. So in our units of measurement section, we should be on the what's called the MKS system. So our standard SI unit for length would be meter rather than inches, feet, or yard, but it would be meters. Mass would be kilogram rather than pounds. Temperature, that is Kelvin. That's the best scale to use for temperature. Fahrenheit is the absolute worst. And then second is that standard unit for time. So of all the countries, we are one of three that is not on the standard system, the standard SI. So we're only one of three. Liberia and Myanmar are the other two. All right, now some conversions here. Don't worry about those just yet. I'll show you what conversions I need you to know. But as you might guess, because we are not on the standard system, we have to make sure we know how to be on the standard system. So we have to learn unit conversions. All right, now before we get there, we're going to talk about prefixes. If you had me for intro, I had you memorize kilo, centi, and milli. Those were the three that I had you memorize for intro. There are three more now for Chem 1. I want you to memorize mega, capital M, micro, which is like looks like a curvy U almost, and then N for nano. Now the book here does it a little bit differently than what we did in intro, and I'm going to let you decide what you're more comfortable with. In intro, what we did is we remembered that 1,000 milliliters was equal to a liter. The Chem 1 way, the way the book does it, is whatever your prefix is, milli, you put 1 with the prefix and then your exponent with the base unit. So 1 milliliter is 10 to the negative 3 liters, which is also like saying 0.001 liters, right? That's 10 to the negative 3. Now, if I take this conversion and multiply it by 1,000, 1 becomes 1,000, 0.001 becomes 1. They're identical, right? They're saying the same thing. It's just one is without scientific notation and one is with. So you can pick whichever one you like better. But in Chem 1, micro, if I were going to do micro, I would say 1 micrometer is 10 to the negative 6 meters. So what you do here in the Chem 1 way is you memorize your prefix, the exponent, and then what you do is the prefix goes with the base unit, right? Meters in this case, or liters, or grams, whatever it is. Then you replace the prefix with the exponent, 10 to the negative 6 for micro, and then there's your base unit. So these two things are equivalent. Micro, 10 to the negative 6, micro, 10 to the negative 6. So it's just another way of expressing these prefixes. All right, so another one, nano. Okay, so 1 nanometer is 10 to the negative 9 meters because nano is 10 to the negative 9. All right. So what we're going to do to practice this is in these first examples, it says restate each of the following measurements by attaching an appropriate prefix to the unit to eliminate the power of 10. So 2.05 times 10 to the negative 6, what we know is looking at what we wrote above, right? 10 to the negative 6 is equal to micro. So all we're doing is substituting 10 to the negative 6 with micro. 4.03 times 10 to the third. If I look back up here, 10 to the third is kilo. So this is going to be 4.03 kilograms instead of 4.03 times 10 to the third grams. All right. 7.06 times 10 to the negative 9 seconds. 10 to the negative 9 is nano. So this would be the same as saying 7.06 nanoseconds. Last one, 5.15 times 10 to the negative 2 meters. 10 to the negative 2 is centi. So that would be 5.15 centimeters. All right, so as the centimeter again in intro, we might remember 100 centimeters is equal to a meter. If you want to use that, that's fine. The way I taught it in intro was centi, like century, 100 years in a century, that made it easy. But you put 100 with the centi. In the Chem 1 way, what it's asking you to do is put 1 always with the prefix, and then we replace the prefix with the power. So 1 centimeter is 10 to the negative 2 meters, which that means 1 centimeter is 0.01 meters. These two conversions are exactly the same. It's just we took 1 and divided both sides by 100, but it's really the same. So it's whatever you're more comfortable with. But this is the way the book is going to do it now, which is just replacing the exponent with the prefix or vice versa. So let's try a little bit more. Next one says, okay, let's restate these measurements by first putting it into proper scientific notation and then looking at a proper prefix. Proper scientific notation is when the decimal follows the first non-zero digit. So 6217, the decimal is going to move 1, 2, 3 spots to the left to become 6.217 times 10 to the positive 3. All right, so when you move the decimal left, the exponent is going to be positive. You're adding. So in the next one, we're going in the opposite direction. We're going to be moving the decimal to the right, which means the exponent should be getting negative. So we're going to take 0.0016, move the decimal 1, 2, 3 spots to the right to become 1.6. Instead of times 10 to the positive 3, it'll be negative 3. And then our unit here was seconds. Now to replace 10 to the negative 3, that would be milli. So this would be 1.6 milliseconds. All right. 0.0717 grams. We're going to move the decimal 1, 2 spots to the right. So it's going to become 7.17 times 10 to the negative 2 grams. All right. And then negative 2 is centi. So 7.17 centigrams. Last one, we got to talk about sig figs here a little bit. So 0 at the end of the value is only a magnitude 0 unless there's a decimal there that tells you it is significant. So the 3,870, that 0 at the end is just there for magnitude. When we put the sign into scientific notation, the exponent is going to tell us the magnitude. So we can basically, when we write this over, it'll be 3.87 rather than 3.870. Now, since we're moving the decimal 1, 2, 3 spots to the left, it'll be times 10 to the positive 3 meters. And that 10 to the 3 is kilometers. So 3.87 kilometers. All right, we'll talk more about sig figs in a minute. So if you had intro, you'll be like, oh yeah, I remember that. But if not, and you're like, what? We're going to circle back. All right, a little bit more here with scientific notation. So this time, what we're going to do is take the prefix, swap it with scientific notation, and then put it into proper scientific notation. So 355 microseconds is the same as 355 times 10 to the negative 6 seconds, because remember, micro means 10 to the negative 6. And then what I would be doing here is moving the decimal. Proper scientific notation is when the decimal follows the first non-zero digit. So I've got to move the decimal 1, 2 to the left, which means I'm adding 2 to the exponent. So instead of negative 6, it becomes negative 4. All right, if I have 1,885 kilometers, that is 1,885 times 10 to the third meters. But if I'm moving the decimal 1, 2, 3 spots to the left, 1.885 times 10 to the 3 plus 3 is a total of 6 meters. All right, 1,350 centimeters. I'm going to move the decimal, well, actually not yet, sorry. That would be 1,350 times 10 to the negative 2 meters, because centi is 10 to the negative 2. And then if I move the decimal 1, 2, 3 to the left, 1.35 times 10 negative 2 plus 3 is actually just a 1. And then my unit of meter. And then 425 nanometers would be 425 times 10 to the negative 9 meters, because nano is 10 to the negative 9. And then if I move my decimal 1, 2 to the left, 4.25, negative 9 plus 2 becomes negative 7 meters. Okay, so what we were doing here was replacing the prefix with the correct exponent and then putting it into proper scientific notation. Proper scientific notation is always when the decimal follows the first non-zero digit. So there's only one number before the decimal. If you move the decimal to the left, you're adding. If you're moving it to the right, you're subtracting. So in this case, we were always moving the decimal to the left. So that's why your exponent was getting bigger. 3 spots to the left, 10 to the 3 became 10 to the 6. Okay. All right. So as far as your prefixes go, make sure you memorize these 6. Okay. So mega, kilo, centi, milli, micro, and nano. Those 6 I want you to know. There are others, but those are the 6 I want you to remember. Okay. Now to talk about density. Density, we've seen this, mass over volume. Typically, units are going to be grams per milliliter, maybe grams per cubic centimeter. That's for a liquid or a solid. If it is a gas, your density unit is probably going to be grams per liter because they are mostly empty space. Densities are very low. So density is another physical property, right? It's a physical characteristic of the matter. It depends on temperature. Density can change, right? If you heat something, molecules spread apart, so they become less dense. So density can change with temperature, but it is independent of the amount of substance, which means it is an intensive property. All that means is that if I have 10 grams of water or 10 kilograms of water, as long as they're at the same temperature, the density is the same. That's what that means, that it's an intensive property. So gases, again, density is going to be grams per liter, but liquids and solids, it's either going to be grams per milliliter or grams per cubic centimeter. All right. Next page. If we're going to find the density of a solid, we know we need the mass of the solid sample and we need the volume of the solid sample. If it's regularly shaped, right, something like a cube where we could measure the length, width, and height, we're going to multiply those 3 and that'll give us our volume. So if I measure my length in centimeters and my width and my height, my volume is going to have units of centimeters cubed. If it's an irregularly shaped solid, something where I can't measure the length, the width, and the height, then for this one, we get the volume by water displacement. All right, so what we typically do here is if you remember doing this in lab, you have your graduated cylinder and you have a little bit of water in there. Then when you put the solid in, the water level rises. And the difference in these 2 volume levels, that tells you the volume occupied by the solid. Right, so that's if it's an irregularly shaped solid where we can't do length times width times height, we'll use the displacement of water. All right, so here's an example. We've got a solid with a mass of 25.22 grams dropped into a graduated cylinder, right? That was this example, that has 15.6 milliliters of water, and the water level goes up to 25.0. The difference in those 2 water levels would be the volume occupied by the solid sample. The way I always thought about it was the volume of water that moves out of the way must be the volume that's occupied by the solid. So I'd subtract these 2 to get the difference. That would be the volume that's occupied by the solid. I've got the mass of the solid. Mass divided by volume, there's my density. Okay, so we haven't talked about sig figs just yet, but if you remember from intro, when you do subtraction, when we're finding the difference in those 2 volume levels, the rule is when you do subtraction, you want to follow the decimal places, dp. Okay, so let me write, because you'll see that decimal places means dp, or dp means decimal places, right? So if I have 25.0 to the 10th place, subtracting 15.6 to the 10th place, my answer is going to go 9.4 to the 10th place. Okay. I've lost a sig fig. I had 3 sig figs, and now I only have 2, but that's okay, because when you do subtraction, what you want to think is, how far past the decimal did I measure? So I can't add a 0 here, right? If you were thinking sig figs, because whatever I was using to measure couldn't read that, right? It doesn't measure that. So that's why it's only going to go to the 10th place. Now, when I go to do the division, right? So this subtraction, that was this step here. Now, when I do the second part and I take my mass divided by my volume, for the division, now what we switch to is we follow the least sig figs. Least always wins. Whichever rule you're following, it's least always wins. If you add or subtract, you look at the decimal places. When you divide, you just look at sig figs. So I've got a 4 sig fig mass, a 2 sig fig volume. So our answer here is only going to go to 2 sig figs for density. All right, we've got more coming about that in just a little bit. When we look at sig figs, it's coming, but we did density first in the chapter. All right. Now, so that's for a solid. So if you remember in lab, maybe with solids, sometimes we do find the volume by displacement, but if it's like a block, we can figure it out by length times width times height. Just depends. But either way, you'll get volume. And then mass divided by volume gets you your density. If it's a liquid, you still need mass and volume. What's a little bit harder this time is the liquid, you can't just squirt it on the scale, right? You need some kind of container to hold it. Since you're going to use that graduated cylinder to measure the volume, you might as well have that use that as the container. So a lot of times what you do here is you start with your graduated cylinder. All right. And again, that is the extent of my drawing skills. And this would just be empty. And we take a mass of that. So this question says, okay, the mass of that empty cylinder is 156.23 grams. Now to that same graduated cylinder, I add my liquid sample to it. I read the meniscus. The volume is 15.0 milliliters. That's the volume of water inside my cylinder. And I take a new mass measurement and it's 169.72 grams. So what I understand is the difference in those two mass measurements is the mass of the liquid that I added. So I'll take the difference in those two mass measurements to get the mass of my liquid. Again, follow the decimal places. Now I can divide that by the volume that I measured using that meniscus. Now mass divided by volume, least number of sig figs here is 3. And there's my density for the liquid. All right, so for a liquid, usually you start with your empty cylinder, find the mass, put your sample in, figure out the volume, look at the meniscus, remeasure the mass. The difference in those two mass measurements gives you your mass of your liquid. Okay, so that's how you find that density for a liquid. All right, last little section talking about sig figs. We're going to do more. I'm just going to introduce, sig figs, then we'll do more on Thursday. So significant figures, you've been hearing me talk about that. You probably remember this from intro. The first, you always got to say, why are we learning this? Because I've heard so many students that are like, I liked chemistry, I just really hated sig figs. It's like, okay, it's not bad. But I like to always understand why. The why is that when you do calculations with data, right? Like our density determinations that we were just looking at. If I have equipment that can get really precise data, then my density determination can be really precise. However, if I use equipment that is just not calibrated to be very exact, like a beaker, right? Beakers are terrible for volume. But let's just say I use it because it's all I've got. Then my density determination, it can't be that precise because the equipment I used wasn't that good, right? That's what sig figs is for. So not only in chemistry are you trying to get the answer, but you're also trying to reveal how well do you actually know that answer to be. And that depends on the equipment that you use to get it. So that's why we look at sig figs. So if it's not a 0, it's significant. That's easy. So non-zero numbers are always significant. Perfect. The zeros are the tricky digit. So we have 0.0206 or 70, doesn't matter. So rule number 1 would tell me the 2 and the 7 are sig figs. Now the zeros, here's the problem. They come in 3 different positions, and guess what? There's 3 different rules. Okay, the zeros before the first non-zero digit. These are not significant figures. They are just placeholders. This tripped me up as a student because I think my teacher said something like, well, sig figs are the measured digits. And I'm thinking, well, the 0 is clearly part of the measurement. It's not like I can just get rid of it and just make this 0.2, right? The 0 is clearly important. what I had to think about was if I go to an electronic scale, I put my substance on there, and this is what the scale gives me. The way I think about it is there's nothing to measure until I get to the 2. There's nothing even registering on the scale, right? So the 2 is the first significant figure. So any 0 that comes before the first significant figure is just a placeholder. That's it. It's just for magnitude. Now, zeros that go between non-zero digits, those are always significant. That makes sense. If I could measure the 2 and the 7, I could measure the 0, right? So that's going to be significant. All right. Now, what about zeros at the end? If they're after a non-zero number and there's a decimal present anywhere, then they will also be significant. So there's a decimal in the value, the zeros at the end, that will be significant. So for 0.02070, there are 1, 2, 3, and 4 significant figures. All right. So 105, 0 between, significant. So there's 3 sig figs. 20.0, the zeros at the end, there's a decimal present, 3 sig figs. 0.0067, zeros in front, just placeholders, only 2 sig figs. 250, 0 at the end, no decimal. That's saying not significant. That says it's just magnitude. So only 2 significant figures. All right. Okay. It's 7:12. I think that's actually a perfect place for me to stop for this first night. So what we'll do is we'll come back on Thursday and pick up where we left off. I'm going to go ahead and stop the recording, but at any point, if you have any questions for me during the week, please let me know. I'll see you back Thursday. Once I hit stop recording, if you want to ask questions, just feel free to unmute and ask me whatever you got. But otherwise, I wish you a great evening and a good Wednesday, and I'll see you Thursday.